Good morning, everyone. We're going to start 4.2. We're going to do two sections today, 4.6, 4.7. We have a guest with us today, Professor Beret. His last name is spelled nothing like it sounds. So, like, it's not Borez, even though that's what it looks like. It's Beret. He's a nice guy. He helped with a lot of the lecture stuff in this class. I've used his rain gutter for that rain gutter regatta problem we did in that optimization with the triangular rain gutter. That was his. Well, he probably got it from somewhere. No, that was yours. So this is a problem you guys learned how to do in algebra. We didn't use calculus techniques. And it seemed kind of silly at the time. You throw a ball straight up. Who the hell does this? Who throws a ball straight up? But in algebra, you haven't learned the trigonometry. This is like if you were to throw the ball at an angle, like playing catch with somebody, it's some physics stuff. You got to throw some trigonometry in there. There's more going on. But simple ball going straight up, straight down. We learned how to do this. Does anyone remember how you would do this in algebra? Find the max height of the ball. It's been a while, I'm sure. Well, we're going to do that. That's not the algebra version, though. This is going to make a parabola if we plot it versus time. If we plot the height of the ball versus time, it starts at 192. It's going to go up in the air, and it's going to come down. Well, it might stop here if he throws it straight up and he's on the top of a building. There's no reason this should keep going to the ground, but there's some max height here. That's at the vertex. You guys learned how to do this before. HK, H is negative B over 2A, and K is F of H. But we're not doing that in here. We're going to do just like you said, take the derivative. So what is the derivative here? Thank you, Dalton. And we set it equal to 0, right? We solve. And I get t equals 2. 2 what? Time is in seconds. It's at 2 seconds. Did that solve this question? No. So how do we solve this question? We plug it back in. I'll just rewrite h here. We had negative 16t squared plus 64t plus 192. And we're going to evaluate h at 2. And all said and done, that should get you 256. And it said the height was in feet. Pretty straightforward, right? This is like one of the first things we learned how to do when we had derivatives. Well, we didn't really apply it till later. We learned how to do the derivatives, but one of our first purposes for it. This is called rectilinear motion. When an object travels along a coordinate axis, travels along a straight line. So you could have it as a good old horizontal number line looking like the x-axis. It could look like the y-axis like it did in this problem. It could be at an incline, but it needs to be in a line. Pause, like make sure you guys catch up on the writing. Wonder where that ball is at t equals 1 second. $48 plus $192 is $240. So if we were going to plot the trajectory or the path of that ball on just that coordinate axis, I'll start at 192. And we know it goes up to 256. And I think 240 is three quarters of the way up. Let's see, we got 56, 64. Yeah, it's 3/4 of the way up would be 240. So the ball starts here at t equals 0. And by t equals 1, it's up to here. And t equals 2, it's up to here. Then the ball starts falling back down, and it should be roughly the same distance back down at t equals 3. And hits here at t equals 4. Although that might be a little bit different. There's some gravity going on in there. But on the number line, the ball's just going back and forth along the number line, right? It's just moving along the number line. What is this, these arrows representing?
Is it its direction? Or?
Its direction is part of it, but it does a little bit more. Because the arrows have different lengths and I've got them posting at different times.
Is it like that feet per second?
It's feet per second. This is velocity or speed. This is measuring the velocity. These arrows are like velocity. This is something you learn in physics. We will do a lot more. These are vectors, the way I did them. And we'll do a lot more with this in Calc 3. Good stuff. Velocity is what in terms of the initial function? We did this before when we first started talking about this chapter. How does velocity relate to position? It's the derivative of position. So we had h of t was our position function. And thus dh dt is our velocity function. Now, velocity has a given direction. We usually don't use velocity in the real world when we're talking about how fast we're going. Because if I tell you I'm driving down the freeway, I might tell you I'm going 70 miles an hour, but I'm not telling you which direction I'm heading. Velocity is speed with direction. And we had that listed here. I had arrows pointing which direction they were going. If we just want speed, if all we care about is how fast we're going, we use the absolute value of dh dt. Because speed is never negative. Velocity can be. That's an important distinction. Speed is always greater than 0. Velocity can be negative. I don't know if any of you all are old enough to remember Michael Jackson moonwalking, but he's facing one direction and moving in the opposite direction. He's got a negative velocity. He's going the opposite direction of the direction he's facing. You remember Michael Jackson moonwalking Baltimore? No. Getting old, Professor Bray. Getting old. I like my evening stats class because I can reference shit from my time, and like many of them are near and close enough to my age that they actually know what I'm talking about. You guys doing all right online? Any questions so far? This is pretty standard. We haven't done a whole lot of new stuff yet. Well, they're still writing. I'm definitely going to wait. I'll let you know, Carlos, he is not here yet. So it may not be today.
Yeah, he said he's on his way, so.
Okay. Oh, Osvaldo's not here. He's online, looks like. He's normally here. All right, you guys ready? Anyone need any more time? While I have this picture up, why are these arrows different lengths? These represent velocity or speed. Why do they have different lengths? This is not a trick question. What? Say it again.
I don't know. I'll say this is time soon.
How far did it go in the first second? Looks like it went 48 feet. How far did it go in the second second?
16.
16. What's happening to the ball? It's decelerating or slowing down is what us humans like to call it. The ball slowing down. The ball's slowing down as it goes up. It's decelerating. which is a fancy way of saying acceleration in the opposite direction. Accelerating in the opposite direction. Acceleration often goes by A. Is a change in speed over a change in time. That's how we define acceleration. Well, change, no, that's not true. Change in velocity. Acceleration also has a direction. What does that mean mathematically? That's what it means. In terms of, can I write this as a formula? How? Let me prompt an idea for you. What's velocity in terms of position? Velocity is a change in position over a change in time. That's our V of t. And it's twitching me. It's killing me not to write an arrow over it. This is the Calc 3 and the physics side of me taking over. It's usually got a direction. We usually put an arrow on it, and I don't like the full arrow because then it cuts into the letter. Deal with it. It represents vectors. That's the description of speed or velocity, right? It's how far you've changed, how much you've moved your position or distance over time. This is the same thing. All I've done is really just change this word up here. How did velocity relate to position? It's the derivative. So V of t was dh dt. What do you guys think A of t is? With all that in mind with what we have here.
Second derivative.
It's the second derivative. Look at Matthew just coming in, just dropping the ball. Like, look at that. I fucking know what I'm doing. Bam! It's like I didn't miss any of this shit. Or ddt of V of t. So we got h of t, h prime of t, and h double prime of t. Position, velocity, acceleration. What is dh dt for our original problem up here? Oh, we did dht. What's the second derivative? I mean, I'll pause and let everybody finish writing. Don, go ahead. It's negative 32, right? It's all that's left, right? It was negative 32 plus 64, 32t plus 64. The second derivative is negative 32, which means what about acceleration? It's constant. Acceleration is constant. I'll write that all down in a second. People still writing this. All right, so. (64t plus 192). We showed that h prime of t was negative 32t plus 64. And as Dalton just said, the second derivative is just negative 32t, which means it's constant acceleration. Not only is it constant acceleration, but it's in the negative direction. If we look at how I drew the building and how we tend to leave do the y-axis, up is positive and below ground is negative, so downward is negative. Is it frozen?
Yeah, that was saying.
There we go. Thank you. So it's constantly accelerating towards the ground. We know that is something in the real world. What is that? Gravity. That's just gravity. What happened at h of, let's look at h of 1. We already said h of 1 was 240 feet. And I'm going to have that little picture up here while we look at it, because we drew pictorially what was going on. What's h prime of 1 and h double prime? Dalton? 32 feet per second and negative 32 feet per second. What?
What are the units on H double?
Feet squared per second.
No.
Feet per second squared.
Yeah.
How about that? I'm like, the numbers are right. What are you talking about? He's shaking me off like the catcher in the game. You're right. Feet per second squared. And we saw pictorially, this is when it happens when it's slowing down. The ball is slowing down. When we are talking about the position function, when we have f of t as a position function, so that f prime is velocity, and F double prime is acceleration. If H prime of t and H prime of t have different signs, H double prime of t have different signs. Ball is slowing down.
Which order they change signs in.
No,
So if
it doesn't.
H prime is negative and then F prime is positive, it's still slowing down.
Yes. In that example, with something where we're talking about height, if the velocity is negative, it means you're falling. But then you have acceleration going the opposite direction. It's like deploying a parachute, where you slow down. Or maybe like jet boosters, where you're slowly, so that you land softly.
So.
So you don't wander.
Same sign.
Same sign's coming in. Let's look at H at 3. H prime at 3 and H double prime at 3. What's going on there? See if I can do the units right this time. We have our functions up there. T equals 3, negative 32 times 3 is negative 96, plus 64. H prime is negative 32 feet per second. And H double prime is also negative 32 feet per second squared this time. I almost did it. Almost did the same error again. Now the signs match though, right? This is a scenario where the ball is speeding up. It's accelerating downward. Its speed is matching its acceleration, so acceleration is improving the velocity. So speeding up happens when the signs match. And when we're doing these derivatives, this is more of the instantaneous velocity and instantaneous acceleration. A lot of times we can talk about velocity or speed. When we say 55 miles per hour on the freeway, a lot of the time, well, unless you've got cruise control set, you're not maintaining 55 miles per hour the whole time. You're fluctuating around it, but within an hour or 60 minutes, you've traveled 55 miles. So these are instantaneous things. Any questions so far? All right. So I'm going to try to draw this graph by hand. You know what? Why do that? Let's just pull it up. So this graph is showing position versus time. So time is along the x-axis and position is along the y-axis. Let's try to model on an axis what's going on here. At t equals 0, where should I put the dot? -5. This is tracking position. At t equals 0, or along the h-axis, it's saying -5. At 2 seconds, so this is t equals 0. At 2 seconds, where is it?
At 0?
So at 0, right? So we got t equals 0 here. T equals 2. And at t equals 4, we're up here. We can see that curve is not straight though, right? We could measure the velocity at any point from between t equals 0 and 4. I could do 5 minus -5 over 4 minus 0. We're getting 10 over 4, or 5 feet, or whatever the units are. 5 every 2 seconds. 5 units per 2 seconds. But that's the average velocity. Instantaneous, we very much have to take the derivative of it. We do not have the equation for that line right here, so that might be a little more challenging, at least at some of the points. And then what's happening? What happens after t equals 4?
It
I
moves
can't
back.
tell if you're. Go ahead.
It moves back
To what?
to 0.
It moves back to 0, and it gets to 0. What time?
At 6.
At t equals 6. I never can tell, Dolan, when you're actually raising your hand or if you're just playing with your hat. You always put your hand right next to it. You're messing with me. And t finally, as t goes to infinity, we slowly tinker, go all the way. Oh, I went too far. I had it right the first time. Goes to -1. So it's a good skill to harvest, being able to pull apart and see what's going on with the graph. If you put it into rectilinear motion coordinates, another way of doing that is looking at it like this, -5 to 5, and not paying attention to the timeline. This is almost like Dance Dance Revolution. The ball's moving, you track where your feet gotta be. All right, you guys ready for some more? Wait, some folks were still writing. I'm getting hasty. Cody, I was talking to Dylan about you, Professor Allen. He said you've been cheating on me and going to him for calculus help. I don't know how I feel about that. He snitched on you. Almost there. Someone's still writing. Just hang in there, guys. All right. We can sit back out. And let's give you guys one to work on for a few minutes, and then we'll go through it together. Let's say the position function is given by S of t equals 2t cubed minus 21t squared plus 60t plus 3. Analyze the motion of the particle with this position function. For t greater than or equal to 0. I like to use S frequently for position. In fact, the only time that I really see them using something besides S is when we're doing it vertically and they use H. They use S a lot. I know none of you guys are going to talk to each other. I did not. I had my wisdom teeth pulled, Cody. That's not fair. I didn't show one weekend. And I told you guys I was having my wisdom teeth pulled. Don't you give me no sass there, boy. So maybe to throw some more questions in for you. When is its velocity positive? Negative? When is it speeding up and slowing down? While you guys are working on it, if you check the latest announcements, I have the Mesa flyer up. Scholarship applications start up shortly and they're due in November. And they've got like a scholarship application workshop, I want to say on the 3rd and then on the 7th. 3rd is Friday. And 7th is what? Tuesday. Tuesday. One's in the morning, one's in the evening. They're worth doing. You can get some decent money out of it. They also have tutoring workshops on calculus and stuff like that. And if you're interested in NASA, there's the flyer that I put up for the NCAS. To make sure everyone's at the same steps, what is S prime of T and S double prime of T? Anybody?
6t squared minus 42t plus 16.
And that's good. Second derivative.
12t minus 42.
12t minus 42. Excellent. Kind of interesting, Professor Beret. Both my morning classes are super quiet like this, even the 10 to 12. Both of my evening classes, except the computer science on Friday, they are a rowdy group. Completely different makeup, too. The algebra one is almost all 18 to 21s. And then the stats classes, I think there's one or two people in the algebra that's over 21. And the stats class, I want to say, is like half and half. But they're all just chatterboxes. Who here needs more time? No one's saying any more time, so let's roll with it. Who wants to help me with this first part here? We've got the velocity function. So how do I find out when the velocity is positive or negative?
Make a side chart.
You make a sign chart, right? What's the easiest way of going about doing that?
Say,
Set it equal to 0. All right, so let's take it. Let's do that. 6t squared minus 42t plus 60 equals 0. You know what? I don't like that these all have, they're even numbers, not just even numbers, they all look like they're multiples of 6. So let's make our algebra a little bit easier, divide by 6. We get t squared minus 7t plus 10 equals 0. You could have done it without dividing by 6, but at that point, I'm looking at quadratic formula. And here I can factor. Like I can see the factors here. What does this factor into?
X minus 6, X minus.
That's incorrect.
T minus 5 and T minus 2.
I'm guessing that's what Dalton was gonna go with. Yes. Cause but I love that you were so like, I got this. He's just Matthew's quick on it. I don't give a shit. I'm okay with being wrong. That's the best way to be in a class. You're here to learn some stuff. All right, so what does this tell me? I factored it. What?
I think inflection points.
Not inflection points so much. Well, they might be. The critical points. Is that Dalton? Is that what you're going with? Dalton, you gotta have that figured out by now. Everybody else blurts out in here. Dalton raises his hand patiently every single time. And when I know that he was going to answer the same as the rest of you, he has. So something like that. So we got 2 and 5. We got negative numbers, but we don't need them. All right, so what am I doing here with the sign chart? How do I help me with this? I don't know what I'm doing.
You're gonna test points, right?
We're going to test points. How do we do that? Dalton. Okay, let's do that. So we're wanting to test between 2 and 5, before 2 and after 5, right? So I think 0 is a great test point. Let's test 0, 3, and 10. We don't really care about the number, we just care about the sign. If we plug it in, and if you plug it into the factored form, it's a lot quicker. 0 minus 2 is a negative, 0 minus 5 is a negative. Negative times negative makes that first region positive. These things often alternate, but that's not a guarantee. So we need to check the rest. T equals 3. We have 3 minus 2 and 3 minus 5. Positive and negative. So that's a negative region. And T is 10. Positive, positive, so that's positive region. So how would I write that in interval notation? When is v of t greater than 0? Oh, interval notation. I caught you guys for that. Done. The 0 to 2 and 5 to infinity. What should I use for symbols here around this? Now, why did you choose 0?
It's negative infinity.
Dalton's actually right. It's 0. But why? It's what we initially asked, right? Analyze the motion of the particle for the position function t greater than or equal to 0. So negative time is not in the domain of what we're working with here. All right, symbolically, what What do we have going on here for interval notation? What goes before the 0?
Bracket,
It's a bracket. Why?
it's included.
It's included. What do I put after the 2? It's a parentheses. The instantaneous, we said this is where we found it at 0. So at 2, the instantaneous velocity is 0. So it's not positive. We're not going to include it. What's the next symbol? Union. And reinforce that algebra stuff on you guys. That's the weakest strength for most calc students. This is algebra. And the 5,
Parentheses.
and then infinity is always parentheses. What about acceleration? How do I tell when it's speeding up or slowing down?
Values for S prime and S double prime.
We can, yes. With what in mind?
Change in sign,
A change in the sign. Between what and what?
first derivative and second derivative.
First derivative and second derivative. So rather than plugging in values, it might be easier to make another sign chart and overlap and see where the signs differ. Does that make sense? We divide that by 6. We've got 2t minus 7. So t equals 3/2, 7/2, 3 1/2. So I'm going to put that. So this was positive, negative, and positive for velocity. What about acceleration? Acceleration is showing up at 3.5. So pick values here. And I've got, it's negative for 0 and it's positive for 10. So if we're looking for regions where it's speeding up, we need to see where the signs match. So I think having more than one of these things, I'm actually gonna do this and show what it's like that. That way I can compare the signs a little bit better. It looks like the signs match from 2 to 3.5 and 5 onward. And it's slowing down from 0 to 2 in union with 3.5 to 5. And with that, let's take like a 5-minute break. Let you guys use the restroom or whatnot. All right, so we finished up with what were we doing? Rectilinear motion. It's been an hour. I've already forgotten the name of what we're doing. It's a weird name, isn't it? Rectilinear. We're coming across something called Newton's method. Now, if you read the book, it's kind of interesting because they go at great lengths to talk at somebody about somebody that is not Newton. I assume this method was designed by Isaac Newton because it's named the Newton's method, but maybe not. Maybe it was designed by this guy, Snell, I think it was. And they just gave it Newton's name because Newton's pretty important, but that doesn't seem right. The idea is this: we've got a lot of methods for finding roots or solutions to equations. Especially quadratics. We can complete the square, we can factor. We can make an XY table. XY table will work here too, but it's just a pain in the butt. Newton's method is good for all of it, but it's like it really shines for third degree and higher. Because this goes into a section that's really under something called numerical analysis. I had to relearn this at upper division. Well, not relearn it, recover it, as we covered a lot more methods that fall in this category. Follows a very numerical approach. The idea is we're looking for these roots here. Let's say that's root 1, this is root 2, and this is root 3. And I've got a nice Desmos clip here for you in a second, but I think showing pictorially and where the equation comes from is beneficial. It's a little bit slow. So what we do is we find a value where actually, let me make sure everyone's got that part written down, and then I'll bring the graph back down. It's not really, the numerical analysis is not really important. It's under calculus still. It's one of our topics. You'll see why I call it numerical analysis in a second. You may or may not like it. It works really, really well for if you're doing it on a computer, coding this up. Follows a nice little algorithm. Okay, so we pick a value that's close to a root by testing points. The idea is test x until f of x is close to 0. You decide how close is close. Let's say you get this point right here and it's x1. So what you do is you come up and see what you've already calculated f of x1. These are different colored pens. I got them in the wrong caps. And you follow the tangent line back until it hits and makes an x2. And presumably x2 is closer to the root than before. So this value has a value of f of x2 right there. x2, f of x2 at that point. And this one is x1, f of x1 up here. With me so far? Haven't done anything mathy yet, other than used subscript. For some reason, we don't do that in other topics that much. What's the equation of that tangent line right there? You can look at that slope equation and start there. That's an easy one to start with. M equals y2 minus y1 over x2 minus x1. We are trying to find the x value that's close to it. So here, let's find x2. It's where the mathy algebra stuff gets going. We clear the fraction. And now I'm going to start plugging some stuff in because I think it makes it a little bit easier. X1 and X2 don't change, but Y1 is f of X1, Y2 is f of X2, and M is f prime of X, f prime of X1. One of these values is really simple though. Looking at the graph, do we know what one of these values is? I didn't actually say its value. See who pulls this up. Looking at my tangent line, do I know any of those values? X1, X2, f of X1, f of X2.
x2.
We're looking for X2.
F of x2,
We know f of X2. Why? What is it?
0.
It's 0, right? F of X2 is 0, so that's really X2, 0. So this becomes f prime of X1. I'll distribute here times X2. Well, no, let's not distribute it. We can just divide. This is just negative f of X1 right now. We'll divide both sides by f prime of X1. And right now we're at X2 minus X1 equals negative f of X1 over f prime of x1. And we finish this bad boy off. We add x1 to the other side. X2 equals x1 minus f of x1 over f prime of x1. Let's let that soak in, give you time to write it. If you know how it works and you know how to find it, and most of you hopefully have the slope equation memorized. You know how to derive it from the slope equation. Even if you don't remember it, you can come up with it again. There's a lot of things we do with the slope equation where we derive them. Point slope form in algebra, we can get that from the slope equation. X2 didn't hit the mark though. X2 got close, so we're gonna rinse and repeat. We'll go up from there, we'll find this is x2, f of x2. Oops. Zoom out. Really? I don't know why I zoomed in that much. That was crazy. And we'll follow that one in. And we slowly get closer and closer and closer until we have our root. But x3 would look like x2 minus f of x2 over f prime of x2 if we did the derivation for it. And we could keep going. Newton's method is this. For n equals 1, 2, 3, and onward, x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. That is Newton's method in all of its glory. The left side is only n plus 1. The right side is only n. So you can find the next step based entirely on the previous step. And you keep going. Continue until f of xn is approximately 0. Or close enough to 0 that you're comfortable with it being the root. Within some margin of error. This, at this point, Becomes a lot of calculator work or computer work. You're gonna hate it if it's calculator work. If it's computer work, it's not too bad once you've got the computer set up to do it right. You guys ready to look at an example? Let's find a root for e to the x equals 3 minus 2x. When you have things on different sides, find a root. We'll leave that formula up there. When you have things on different sides, you really want to gather all terms on one side. And then we make that equal f of x. So I'm going to subtract 3 and add 2x to both sides. We had it equals 0, but that's where we start assigning it the value f of x. Let's take a look at what like x equals 1 looks like. So f of 1 is e plus 2 minus 3. And this is about 2.7 plus 2 is 4.7. This is about 1.71. And you may go, well, I don't know, is that close enough? I don't know. Let's take a look at like f of 0. E to the 0 plus 2 times 0 minus 3. I've got 1 minus 3 is negative 2. Why are you shaking your head, B? No reason? Am I losing you? You're bored? So f of 0 is down here and f of 1 is up here. I know it crosses somewhere in here. That's called the intermediate value theorem. That's stuff you did a long time ago. We know there's a point between 0 and 1. Let's use Newton's method to find it. Because do you want to try to solve this? Like, how would you even go about solving this? I don't know. Doesn't sound like fun. So let's pick a point. Let's start with x equals 1. This is really e minus 1. If we use 1.71, we're going to have some rounding errors in there, but I'm okay with that if you're okay with that. So our next step, remember we've got x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. So it looks like we need f prime also, don't we? To proceed with Newton's method, we need f prime. So what is f prime of x?
Give x plus 2.
E to the x plus 2. And to find x sub 2, we need f prime of x sub 1. We've got x sub 1 is 1, f prime of, or f of x sub 1 is about 1.71. We need f prime of x sub 1. That is e to the first power plus 2, which is about 4.71. Not exciting by hand, is it? So this is a calculator work. X sub 1 is 1 minus, I'm just plugging in the stuff I have here. The F goes on top, that's 1.71 on top. We've got 4.71 on bottom. Maybe we should use some more decimal places. Let's do some more decimal places. Where's my E? There's my E. E to the first power minus 1. .71 8282. So this should be 4.71 8282. And I've got 6 decimal places, so we'll go to 5 decimal places here. Do 1 decimal place past what I wrote. All right, so 1 minus 1.718282 divided by 4.718282. To 5. What is f of x2? Let's see what its value is. So e to the 0.635825 plus 2 times 0.635825 minus 3. I'm getting 0.16. 0.230 to 6 decimal places. We're closer to 0. See that? F of x1 was 1.71. F of x2 is now a lot closer to 0. Let's find f prime of x2. Exciting, right? So if you're like, I like letting my calculator do all the work, this is a good section for it. It makes it nice if you're doing programming, you can code this up algorithmically and just have it go until x sub n plus 1 minus x sub n is approximately 0. All right, so let's look at what x sub 3 is going to look like. Just hit the thing with my wrist. We've got x sub 2 minus f of x sub 2 over f prime of x sub 2. Which equals 0.635825 minus 0.160230 over 3.888580. Just compiling the rounding errors here. 60230 divided by 3.888. You guys see how this process works? Let's speed this process up with Desmos. Once you've got this written down. I felt it was important to do a couple steps to show you what it looks like by hand. As you'll probably have to do one by hand for the test. But maybe I'll only make it like 1 or 2 decimal places. Maybe 3. I don't know, V, what do you think? Does 6 sound good? You don't want to go 6 decimal places, like take up like 3 pages of, are you sure? Matthew, what about you?
Do one.
1, I can do 1
Yeah, maybe, and bonus question.
as a. Anyone still writing it down? Yes, I see pencil still going. Take your time. Oh, people are already done. All right, let's come over here and flash over to Desmos. All right, this was coded up, I believe, by Professor Beret. I don't think he's plagiarized or stole this from anyone else. I stole this from, well, he gave it to me, so it's not really stealing, right? So this, we have our e to the x plus 2x minus 3, and it's got Newton's method coded up. We said x sub 0 or x sub 1 equals 1. And we can see that it's going up to here. It's hitting the line. The tangent line comes down here, and it hits right here. And that's what we had to 4 decimal places. And you can, it looks like you can see the tangent line here is red. Well, I can see it because I can look at the computer screen. I don't know if the projector's showing it well. But if we zoom in close enough, look at this. That's what we got for x sub 3 to 4 decimal places. And presumably we can go even closer, but this doesn't get closer than 4 decimal places on Desmos. So I don't know that it's going to show any better than that. Wow, I zoomed in really close. I'm still scrolling out. Good God. All right. Wow, that was a lot of scrolling. So depending on how close your estimate is, kind of shows like how many times you might have to do this. If we do something like x sub 0 is 2.5, our f of x value is, don't scroll up, just work smarter, 14. That's not really close to 0, so that's x2 being 2.5 isn't a good starting value. And it shows because it takes more iterations to get down here and get close. But it will keep getting closer. It's kind of neat, right? It's a neat method. Doesn't always work. And you'll know when it's not working, because your values just keep diverging away from it. You're not getting closer to a number, you're getting further and further from a number. I've got one of those loaded too. This is the bad juju graph. So here, this is the function, the cube root of x. And if we start with x sub 0 equals 0.75, or maybe we start with 1. Let's start with 1. We come up here, and the tangent line leads us over to -2. And we do -2. It takes us there. The tangent line takes us over here. And we got a point over there. Then we go use the Newton's method. We go up, this is our new x. We go up here. We find the tangent line. It leads us way over here to -8. We follow its negative, or follow Newton's method here, drop down to here. It takes us way over here to 16. So you can see we're nowhere near the root. We're getting further and further from zero. So Newton's method doesn't always work if you don't have values that are close. What makes a good starting value here? We need something where the next value is closer than the previous value. So I need to edit the scale here. Does it ever? Does it ever give us a value that's? Even 0.0001 takes us further away. 0.0001, 1/10,000th is still 0 away. Nothing. It's not going to work anywhere. It's not going to give you the root. You can't pick a value close enough that the next step leads you closer. So the Newton's method doesn't always work, but when it works pretty well. You guys have any questions? Let me give you guys one to try in class. Let's do f of x equals x to the 4th power plus x minus 3. I recommend start with x equals 1. And maybe go to 2 decimal places. So that when x sub n plus 1 equals x sub n to 2 decimal places, you're good to go.
You switched.
Oh, yeah. Thanks, Jose. Work on that for a few minutes, then we'll this is calculator work, quick calculator work, actually. Well, I don't know how quick it is. But it's just a simple exponentials or a polynomial. So at least you're not having to find the E button. Do 1 decimal place. I don't know that we have time to go to 2 decimal places with the 10 minutes we have left. You stayed for the whole presentation, man. I'm surprised. Want to make sure you're not leaving this calc class as some inferior instructor. Professor Beret taught this course last time it was taught. He normally does mornings and I do evenings, but I thought, you know what? I wanted to torture Voldemorta, so I would teach this class. Cody, I'll be there this Saturday. I was there this last Saturday, and I think next Friday, not this Friday, but next Friday is a holiday. But Saturday, what is it, Veterans Day, something like that? I don't know what day it is. It's probably Veterans Day. Yeah, Labor Day is the one in September. Veterans Day is November, right? But Saturday is not a holiday, so as long as
Yeah.
Tess lets me do it, I'll have the Mesa Center open next Saturday also.
Next Saturday is Veterans.
Oh, is it? We're
Yeah.
just celebrating on Friday? We'll see if she lets me do it. I don't have any veterans in my family. So I don't wanna go to a parade. Well, I'm sure I do, but they're not still alive. Someone in my history had to have fought in a war. If you or anyone in your family is a veteran, thank them for me for their service, their sacrifice. It is greatly appreciated. I love the freedom to be able to sit here in front of you wearing a t-shirt and if I choose shorts and sandals and socks. Well, sandals and socks is the only thing I can't teach in. Because my wife will hide the sandals if I pull out the socks. She detests sandals and socks and won't let me wear them. I think they're phenomenally comfortable. You have the breathing room of sandals, but your feet aren't exposed like socks. You'll be there this weekend next? Okay. Cody, let me make sure with Tess that I can keep it open next weekend because it is Veterans Day. But definitely this weekend will be open. And I'll let you guys know on if she lets me know by Thursday, I'll let you guys know by Thursday. For next week. While you're looking at it, might be a good weekend for other people to come in because guess what we're doing next week? Yay! Another test. I'm not seeing any enthusiasm. WTF? There it is. Thank you. Yeah, I'll have something for practice up by Thursday. I'm working on that tomorrow. I don't even have your test ready. So yeah, this is Wednesday's chore. Making up practice exam material and I'm sure practice exam stuff's easy. I got list after list after list of previous instructors' exams and I can pull questions from theirs and did you guys like the last review thing where we had like 20 questions and I did all the entire video showing how to do them all? Did that work? I think that's a good approach. On Thursday, we'll do 4.8. I'll have the review ready for you and I'll make the video maybe Friday morning if I have time Friday morning before I go torture V some more Friday afternoon, or I'll do it Saturday afternoon. She's the only sicko that took me for 2 classes. I don't even need a calculator for this. Did I make this too easy with 1 decimal place? I think I did. One minus -1/5 is 1 plus 1/5, which is 1.2. All right, I guess this one isn't as easy. 1.2 to the fourth power. Let's see, 0.04, 0.008, 1.0016. See if I can do this one in my head. 1.0016 plus 1.2 minus 3. 2.2, we got negative 0.7984. Did I do that right? Probably not. Nope, nowhere near it. That was wrong. Oh well, it's good practice. Try to do that mental, yeah. It should say fourth. I tried to cheat and did 0.2 to the fourth power. 1.2 is a little bit different. Oh, sorry, that's f of 1.2 right there. F prime of 1.2. We've got 4 times 1.2 cubed plus 1. Which is 7.912. Switch colors for x sub 3. X sub 3 equals x sub 2, which is 1.2, minus f of 1.2, which was negative 0.36, over f prime of 1.2, which was 7.912. Which is 1.2455. So to 2 decimal place or 1 decimal place, 1.2. Something's off. That's not what I have in my notes. One of these is off. Which one of these? You get that?
That's what I got. Yeah.
So 1.1654 and some change, and that's still approximately 1.2. If you go far enough, you get 1.16403540. They start matching up. And it's 10 o'clock. You are all free to GTFO. Get the fuck out. Have a good day. Happy Halloween, guys. I'm glad to see no one else dressed up. I feel better about myself. Now, don't go out trick-or-treating, but this is what I strongly encourage you to do. Go out and look for people that are too old to trick-or-treat. Like people walking around in their football jerseys and shit like that. And take their candy. Because you know they're out stealing candy from little kids. Punking little kids. Go out and punk them. Take their candy. That's my recommendation for a happy Halloween. Have a good time. Have a good party or whatever. I'll see you guys on Thursday.